A very warm good afternoon, everyone. I am Anjali Sharma, and today, along with Himanshu Gupta, we will be going to host today's Knowledge, presenting you a brief session on Cloudstate, distributed state management for serverless. Before going into the details of the agenda and the details of the session, let's just first go through some of the knowledge etiquettes. So the first one is the punctuality. So we request all of you to please join the knowledge session a little earlier than the designated time, and you should, as a general courtesy, it would be better if you ignore joining the knowledge after a 5 minutes threshold post the session start time. The second one would be to keep a silent mode on your mobile phones as well as your screen unless there is a query or concern. And avoid chit-chat during the session, as it can create disturbance for the presenter as well as for the audience. And the most important one would be the feedback. So I request all of you to please submit constructive feedback for all the sessions, as it is very helpful for the presenter for the next time. So let's start with the agenda for today's knowledge session. First, we will look into what is serverless computing. Then we will look into the limitations of serverless platforms. Then we will look at why there is a need to rethink CRUD operations. And then we will learn about Cloudstate and its architecture. And finally, we will look into how we can work with Cloudstate. In the early days of the web, anyone who wanted to build a web application had to own the physical hardware required to run a server, which is a cumbersome and expensive undertaking. Then came along cloud computing, where a fixed number of servers or amounts of server space could be rented remotely. Developers and companies who rent these fixed units of server space generally overpurchase to ensure that a spike in traffic or activity will not exceed their monthly limits and break their applications. This means that much of the server space gets paid for can go to waste. Serverless computing allows developers to purchase backend services on a flexible pay-as-you-go basis, meaning that developers only have to pay for the services they use. This is like switching from a cell phone data plan with a monthly fixed limit to one that only charges each byte of data that actually gets used. The term serverless is somewhat misleading, as there are still servers providing these backend services, but all of the server space and infrastructure concerns are handled by the vendor. Serverless means that the developers can go do their work without having to worry about servers at all. Some of the examples of serverless computing is Amazon Lambda, Microsoft Azure, and Google Cloud Functions. So these are some of the platforms which provides serverless services. Now let us look into the advantage of using serverless computing. The first one is simplified scalability. Application built with a serverless infrastructure will scale automatically as the user base grows or usage increases. If a function needs to be run in multiple instances, the vendor server will start up, run, and end them as they are needed, often using containers. As a result, serverless applications are able to handle an unusually high number of requests just as well as it can process a single request from a single user. Whereas a traditionally structured application with a fixed amount of server space can be overwhelmed by a sudden increase in usage. Next point is low latency. Because the application is not hosted on an origin server, its code can be run from anywhere. It is therefore possible, depending on the vendor used, to run application functions on servers that are close to the end user. This reduces latency because requests from the user no longer have to travel all the way to an origin server. Third is easily deployable. Using serverless infrastructure, there is no need to upload code to servers or do any backend configuration in order to release a working version of an application. Developers can very quickly upload bits of code and release a new product. They can upload code all at once or one function at a time, since the application is not a single monolithic stack but rather a collection of functions. Next, and the most important point, is cost effective. As in a pay-as-you-go phone plan, developers are only charged for what they use. Code only runs when backend functions are needed by the serverless application, and the code automatically scales up as needed. Provisioning is dynamic, precise, and real-time. In contrast, in a traditional server-full architecture, developers have to project in advance how much server capacity they will need and then purchase that capacity whether they end up using it or not. Next is no server management required. Although serverless computing does actually take place on servers, developers never have to deal with the servers. They are managed by the vendor. This can reduce the investment necessary in DevOps, which lowers expenses, and it also frees up developers to create and expand their applications without being constrained by server capacity. Next, so far we have talked about what serverless is and how we got here, and told you the many wonderful ways that serverless will make our life better. So far it's been all smiles, but now we need to tell you some hard truths. So some of the limitation, the three main limitation I would say of serverless platforms is stateless, latency, and no addressability. Stateless. It may seem obvious, but in a serverless application, the management of state can be somewhat tricky. Aside from the components that are explicitly designed to be data stores, most serverless platforms are effectively stateless. Stateless components must, by definition, interact with each other, stateful components, to persist any information beyond their immediate lifespan. As we'll talk about in a very next section, that interaction with other components inevitably introduces latency as well as some complexity. What's more is that stateful serverless components may have very different ways of managing information between vendors. Also, while statelessness is the fundamental rule in many cases, oftentimes specific implementations, especially fast platforms, do preserve some state between function invocations. This is purely an optimization and cannot be relied upon, as it depends heavily on the underlying implementation of the platform. Unfortunately, it can also confuse developers and muddy the operational picture of a system. The next one is latency. Serverless faces two kinds of latency challenges: cold starts and high tail latencies. First, when the user request arrives, the serverless platform needs to load the function, which is one of the causes of high tail latencies. Because it's not constantly running, serverless code may need to boot up when it is used. This startup time may degrade performance. Cold starts are avoided by keeping one copy running, by forecasting when the first call happens, or by improving the startup time of the code. While serverless platform providers are always improving the performance of their underlying infrastructure, the highly distributed, loosely coupled nature of serverless applications means that latency will always be a concern. For some classes of problems, a serverless approach may not be viable based on this limitation alone. Next one is no addressability. So another limitation of FAS is that quite often functions simply have no direct addressability, which means that they can't communicate directly with each other using point-to-point communication. This forces developers to resort to publish-subscribe, passing all data over some slow and expensive storage medium. Publish-subscribe provides a model that can work well for event-driven use cases, but yields too high latency for addressing general-purpose distributed computing problems. Now let's move ahead to look why there is a need to give a second thought to CRUD. So CRUD is basically an acronym for the 4 general operations that a database performs: create, read, update, and delete. Every web application uses CRUD operations of a database for storing or retrieving data. However, accessing the database or doing CRUD operations in a serverless computing world is totally different, because every user function that needs to read or write data would need access to the database. Unconstrained database access means that the user function itself needs to manage nitty-gritty details about the data access and storage, and you are thereby moving all the operational concerns from the serverless framework to the user function. Now it's hard for the framework to know the intention of each access. For example, is the operation a read or a write? Can it be cached? Can consistency be relaxed, or is strong consistency needed? Can operations proceed during partial failure? Instead, if we understand these properties, then we can make better decisions automatically. For example, write ops are fast than read operations, and read operations are slow. So we will add more memory to the database. Reading immutable values, then we will add caching. Writes must be serializable, then we will add sharding or single writers per entity. So next, let's see what abstracting over state means. So when we try to use this existing CRUD strategy, which we just saw, that is providing unrestricted access to the user function for the whole database, then maintaining the state becomes difficult. If you ask why, because we can't give access to the whole state to a user function, as that would require us to pass the whole state to the user function and send a whole updated state from the user function. So what's the solution to this problem? It is restricted input-output patterns. So let's see what it is. A probable solution to this problem is the use of data storage or access patterns which will restrict the input or output of data. For example, key value, event sourcing, and Crdts. Let us see and understand what they are. So the first one is event sourcing. Event sourcing ensures that not just the state is updated when a request arrives, but also the event is stored, which makes that change to the state. In event sourcing, the state in is the event log, while the state out is the updated event, which is generated as a result of handling a command. This pattern ensures that the user function updates the state without accessing it directly, and it removes the need to provide direct access to the state to the user function. The next is Crdts. In Crdt, a conflict-free replicated data type is a data structure that is replicated across multiple machines, where the replicas can be updated independently and concurrently. When any one of the replicas is updated in it, state in is a stream of changes to the state, and state out is also a stream of changes to the state. The advantage of this pattern is the same as the event sourcing. There is no direct access to the state, as it just needs the changes done to the state so that it can update the state with the help of them. The next one is the key value. This is the latest complex and the most used pattern, as in it, the key is the state out and the value is the state in. In terms of advantage, this pattern is slightly different from the previous two patterns as it accesses the state directly, but not the whole state. Instead, it accesses the state modified by the just previous user function. So this was all about the limitations of serverless computing and restricted input-output patterns. Now let us look into how Cloudstate is providing a solution to overcome the limitations of serverless computing, and for that I would like to hand over to Himanshu now.
We have already seen in previous slides, like event sourcing, Crdts, like conflict-free replicated data types, key value storage, P2P messaging, and CQRS read-side projections. Now, all these patterns are allowed or supported in Cloudstate because Cloudstate does not restrict us to follow one pattern there, right? Because there can be multiple patterns which user or which their developers want to follow, right? And the last thing is, it is polyglot. Now, what polyglot means is that, like, Cloudstate uses gRPC for all of its communication with external entities like user, with internal entities like from machine to machine, within services, right, and those kind of things. I should not say within services, but like within different machines, right? It just uses gRPC for that one. And the beauty of gRPC is that, like, it can be implemented, or we can use any language that we want to use. Either it is a JavaScript or Java, Dart, Go, Python, Spring Boot, .NET, whatever you can think of, which supports gRPC, you can use that language. So it's not restricted to just like a group of like developers or a community. Anyone can use it. So that's what really Cloudstate is. Now, moving further into the Cloudstate, let's take a look at its architecture. Right? Cloudstate is built over on top of K8, that is Kubernetes, Knative, GraalVM, gRPC, and Akka. Now, having all these things mixed up into this one, I should say, framework allows a lot of capabilities that are not present in a serverless architecture. So if I point, in a normal serverless computing application, there is a user, right? Then there can be an ingress or an application gateway, kind of thing, and then directly you would be directed towards your server or your function, right? But in case of Cloudstate, we have a Knative stateful serving in between, which handles all the Knative events, right? And the good thing here is that none of the function can interact with the distributed database, or I should say with the database. Only one entity, that is like the Knative stateful serving, can access the database. Now, what are its advantages? So one of the advantages is that, like, for example, in future, if we have to add another serverless function, right, into our Cloudstate services, then what we can do is we just need to focus on the business logic there. That is just the function that we need to process, or the kind of processing that we need to do, and that's it. We are done, right? We can just add it here, connect it with the stateful serving, and that's it. Knative stateful serving will take care of all of its input-output messages and handle all the data that needs to be persisted into the database. That's it. Next thing is use of gRPC channel there. Now, gRPC channel is used for everything here, right? Like for communicating with the knative stateful serving, right? Of course, you can also use an HTTP connection here, but for all the communication that happens internally, gRPC is used, right? A gRPC channel is used for both inbound and outbound communication, which goes through sidecars. Sidecars are present in the knative stateful serving, right? Also, a single gRPC channel is used per service or entity, which allows the infrastructure to safely cache the entity state in memory. Now, what it means that for every single entity, or I should say one service, entity is like this service, only one gRPC channel is used. Why? Because this particular function can be handling a state which we need not to be altered by another function, right? That's why. So that's why it uses a single channel per service or entity. Now, what is really present under the hood of that knative stateful serving? If we talk in very simple terms, then it is nothing other than a Akka cluster under the hood that works for the knative stateful serving, right? Why we are using Akka cluster here? Because it provides durable Akka actors, which in turn supports several data models, storage techniques, and database access techniques, which we can easily use for maintaining the state, or for caching the state, or caching the data there, right? This also shields the user from the complexities of Akka cluster via a set of sidecars, which bridges the user code to the backend state and cluster management. Now, what it means that while developing a function, like for example, if we are developing a simple shopping cart processing function here, right? Like this shopping cart functionality is having just addition and deletion functionality, and that's it. We don't, or the developer doesn't have to care about what needs to be in memory, right? They don't have to take care of like what will be saved in the database and what should that user cache and those kind of things. That all that responsibilities goes to the Akka sidecar for that particular service or that particular serverless function, right? And the Akka sidecar takes care of all the activities, like what all events are going in, what all events are coming out of it, and how to manage the state, what data needs to be persisted into the database, and those kind of things. And in case of a failure, like for example, there is a node down or there is a machine down which was running this particular service, then when that node or when that same particular service gets up on another node, then Akka sidecar is also responsible for building up the state or repopulating that cache from the database itself. So in a way, we are fault tolerant and resilient here. Now, the next step would be how to work with Cloudstate, right? So the first step of working with Cloudstate is to select your programming language, right? And that is quite easy here, as we have seen that the Cloudstate is nothing but, Cloudstate is polyglot, right? Which means that we can use any programming language to build services or applications in it, whichever supports gRPC. So for example, we can use Dart, Go, Java, Kotlin, JavaScript, Spring Boot, .NET, and those kind of things. And if there is a language which is not present in that currently supported programming languages of Cloudstate, then we don't have to even worry about it. We just have to check whether that particular language supports gRPC or not, and that's it. Cloudstate community can provide a connector for that one, like very easily. So it's like it can speak any language that you want it to speak, as long as it supports gRPC. The next step is, and in fact this is the last step, and that is to focus on the business logic. That's it. As we have mentioned in the architecture slide, that we just have to focus on, we just have to build the function, right, that is going to do the processing. So the next step of working with Cloudstate is to focus on the business logic itself, right? You don't have to take care of the nitty-gritty details like how the cache will be maintained, how the events are going to get in and out, what needs to be processed and what not needs to be processed. You just take care of the processing itself. That's it. You just need to provide a Kubernetes environment and run your Cloudstate services on it. That's it. It's as easy as it can get. Now, this is a typical structure of a Cloudstate service that is present on like that we have for most of the serverless computing, apart from having just this Akka cluster in between. So let me explain the component, like one component at once. So first component that comes into play is the service mesh, or I should say the ingress, right? Now Cloudstate expects the traffic to be distributed evenly across its pods. Why? Because it is not a load distributor or a load balancer there. It expects something to be balancing that load for us. So for that, I think we can use like Istio, Knative, or just regular cluster IP service communication can be used there, which can divide the load between different nodes of the Cloudstate service. Then Akka sidecar. Now it is injected by the Cloudstate operator itself, so we don't have to worry about it. All the requests go through it, right? Even whenever there is a response from that service, it also goes through the Akka sidecar only. So all the input and output goes through the Akka sidecar. Now, what's the benefit of that? In case Akka sidecar needs to persist any data into the distributed database, then it can take a decision on that basis, right? And see whether it has to persist anything into the database or not, or what data it needs to cache and those kind of things. Also, it isolates our function from having interaction with the database, right? Now, generally in serverless computing, what happens is that whenever we are developing a serverless function, or I should say just a function, then we also have to think about like what data needs to be saved in the database and provide some connected to it, or I should say a simple API to it, through which it can interact with the database, either for just reading or for writing or for both, right? So all that responsibilities, all that load has been taken care of by Akka sidecar itself. Now the next comes is the FX, that is the function that you want to implement. And that's it. Just focus on what you want to implement, write your processing logic inside it, and you're done done, right? And deploy it, and that's it. And the last one comes the distributed database. Now this is the place where the state is persisted in form of events. Now why we are saying events? Because Akka sidecar takes care of all the requests and response that goes through the Cloudstate service. Why? So it doesn't mutate the existing data. What it does that it keeps all that data in form of the events, so that in case there is a failure and it has to build that state again, it just goes to the database, checks what was the data, what was the state of the database, what was the state of that particular I should say entity, or for example, like if we are having a shopping cart service, what was the state of that shopping cart? How many items were there, or was it empty? It will just grab those events, rebuild that particular state, and we are done. That's it. It's that much simple. So this is how a typical Cloudstate service structure looks like, right? These are the only components that are required in it, and we can easily run it on a Kubernetes environment easily. And that's why it is like cloud native, and we have already seen that the cloud native applications have quite good capabilities, not just in terms of like processing, but also in terms of like cost saving and flexibility of enhancing itself or scaling itself for the future. So I think these are just the references for now. And if there are any questions, then please let me know so that we can answer them. Okay, so I take that as a no as a no. So thank you everyone for your for your time. And please do submit your feedback for this session, and so that we can improve next time. Thank you, everyone.